In this video, we will look at the various facets of cache performance. The various design options for cache design have different performance implications and many performance trade-offs. We will make a beginning towards understanding these in this video. Here is an outline of what we will see. First, we will understand the three kinds of cache misses, the classification of cache misses into three kinds. An important design parameter in a cache design is the selection of its block size. We will understand the performance implications of this parameter. There is a performance trade-off between choosing a joint or unified instruction and data cache versus separate instruction and data caches. We will understand this. Another important parameter in cache design is the associativity. We will seek to understand what things are affected by this parameter of associativity. Each of the last two bullets here involves an interesting idea. We will look at the design of the cache to main memory interface and specifically the idea of interleaved memory. Then we will look at this idea of multi-level caches or a hierarchy of caches. We will see that this idea of multi-level caches gives us good flexibility in cache design, ultimately resulting in better program performance. Cache misses can be one of three types. The first type is called compulsory miss. This is the kind of miss which is caused the first time a block is accessed. When a program starts executing, all of the program exists only in main memory and the cache memory is empty. It is logically empty. Of course, there are always some bits in the cache memory. What it means to say that a cache is empty is that all the blocks are marked invalid. The other terminology which is also used is to say that the cache starts cold. The second kind of miss is called a conflict miss. This is a miss caused due to insufficient set size. That is, the set of blocks becomes full and due to this reason, one block gets kicked out, after which it is accessed. And when that block which got kicked out is accessed, that miss is known as a conflict miss. And by definition, we say that there cannot be any conflict miss in a fully associative cache because the set size is already as big as possible. That is the entire cache itself. The third kind of miss is known as a capacity miss. This is caused because of insufficient cache size. By definition, capacity misses are those non-compulsory misses which will happen in a fully associative cache. These are the only three kinds of misses which are possible in a cache, and these are called the three C's because each of the types begins with the letter C. Now, in a particular cache instance, it is easy to classify compulsory versus non-compulsory misses. To classify a miss as conflict versus capacity, we have to analyze the situation. Supposing that the cache had been fully associative, would the miss have happened? If it would have happened, then it's known as a capacity miss. If it would not have happened, then it is known as a conflict miss. We now have the terminology to discuss the performance implications of various parameter choices. First, let us discuss the effect of increase in block size. Think and tell what is the effect of increase in block size. Specifically, what is the kind of miss of the three kinds which will potentially go down with increase in block size? With increase in block size, we are increasing spatial locality, which means that we have the potential to decrease the number of compulsory misses. Of course, increasing the block size is not going to be good from all perspectives. What do you think is going to be the bad effect of increasing block size? What kind of miss is going to increase? Well, for a given cache size, with increase in block size, we have lesser number of blocks, so the conflict misses are going to increase. Irrespective of the set size, the number of blocks within a set is going to decrease, which means that we are going to have more number of conflict misses. What is the other bad thing which is going to happen with increase in block size? With increase in block size, we have more work to do during each miss. That is, we have a higher miss penalty. So these are the qualitative effects of varying the block size parameter in a cache. As to what final effect it will have on the program performance can be analyzed quantitatively, and such quantitative analysis we will postpone to a subsequent video. To test your understanding, what do you think is going to be the shape of the curve which represents the miss rate as a function of the block size? For a typical program, the miss rate as a function of block size will look something like this. The miss rate on the y-axis and the block size on the x-axis. As the block size increases, the miss rate will slowly decrease, and after a point it will start increasing. The reason why the shape is like this is that until this point in the curve, the lowering of the compulsory misses is the dominating effect, but beyond this point, the increase in the conflict misses is more dominant than the decrease in compulsory misses. So the overall miss rate decreases until a certain point and then increases. Most programs in practice exhibit this kind of miss rate versus block size behavior. While the optimal block size in the previous graph may be optimal from the perspective of miss rate, it may not be optimal from the perspective of miss penalty. What is the optimal block size to reduce the miss penalty? Well, to minimize the miss penalty, we must have block sizes of 1, which is clearly impractical because that would result in no use of spatial locality at all. So we want to look at techniques to reduce the miss penalty even with an increased block size, a block size of greater than 1 word. One thing we could do to reduce the miss penalty is to do what is known as early restart. In the usual case, the processor has to wait until the entire block is loaded from main memory to cache memory. In the early restart scheme, what we can arrange is that the processor proceed as soon as the required word is in the cache. That is, the processor ends its stalling as soon as possible and proceeds, while the cache controller is in charge of filling up the remaining block with the remaining words. With a more complicated cache controller, we can do something better. We can even arrange that the critical word, that is the word which the processor requires in the block, comes first, irrespective of where in the block this critical word is, and then the cache controller fills up the remaining block with the relevant words. Obviously, these schemes will have the implication that the cache controller would have to be more intelligent and more complex to do such things. Next, let us look at the performance implication of this design choice of joint or unified instruction and data cache versus separate instruction and data caches. Now, in terms of the hit rate metric, which of these two design choices do you think is going to have a better hit rate? If you compare the hit rate of separate I and D caches of size X each and the hit rate of a joint or unified instruction and data cache of size 2x, the latter case, the unified instruction and data cache of size 2x will typically have a better hit rate. This is because of the larger cache size and the lack of strict segmentation of instruction and data into separate parts of the cache. Then, what do you think is the performance disadvantage of having a joint or unified instruction and data cache? Well, as we discussed during the pipeline design, a joint instruction and data cache will lead to more structural stalls in the pipeline and hence lower instruction throughput. Once again, these are the qualitative implications. As to what this finally quantitatively means in terms of program performance, we will have to look into in detail. Another important parameter in the design of a cache is the level of associativity in the cache. What do you think are going to be the advantages and disadvantages of increasing the level of associativity in a cache? The advantage with an increased level of associativity in a cache is going to be that we will have lesser number of conflict misses. However, this will come with a price. Since the number of comparisons as well as the size of each comparison, that is the tag size, is going to increase with increased associativity, there will be a corresponding increase in the hit time. Let us understand this reduction in conflict misses a little bit further. What do you think will happen to the overall miss rate as we keep increasing the level of associativity? That is, what will be the shape of the graph of the miss rate plotted against the level of associativity? With increase in associativity, the miss rate is going to decrease. However, with higher and higher levels of associativity, the relative benefits of increasing associativity is going to be smaller and smaller. In other words, the miss rate versus associativity curve is going to flatten out after a while. This is because increase in associativity decreases conflict misses, but in a given program, there are only a certain number of conflict misses to remove. Let us next look at the design of the interface between the cache and the main memory. The interface between the cache and the main memory comes into play during a cache miss. During a cache miss, the cache has to load a block of words from main memory to the cache. And the reason why this interface is important is that it dictates the miss penalty, which is an important performance metric. The miss penalty is the time to load a block of words from main memory to cache. There are three main steps which will happen on a cache miss to handle the miss. First, we have to send the address to memory, the address of the block of which the missed word is a part. Once the main memory has this address, it will take some delay for the DRAM to return the word which is resident at the given address. This is the DRAM access initiation latency. And then after this latency, we actually have to read the word from main memory to cache. So just to test your understanding, who or which entity is going to be responsible for sending the address to main memory? That is this first step. The cache controller is the one which is going to be responsible for sending the relevant address, block address, to main memory. Now, in this sequence of three steps, the first and last steps involve what are known as bus transactions. There is a bus interface between the cache controller and the main memory. We will learn more about bus transactions later as part of input-output systems in this course. Of these three steps, the middle step, the DRAM access initiation latency, is typically the one that will dominate. For example, let us say that the first and last steps take 1 cycle each, whereas the middle step takes 15 cycles. Further, let us say that the width of the interface between the cache and the main memory is 1 word wide. So if the CPU and the cache are both part of the same chip, this will mean that there are 32 lines going between this chip and the DRAM chip. In this scenario, can you tell what is going to be the miss penalty for a block size of 4 words? So for loading a block of 4 words, we have to operate 1 word at a time. That is, the cache controller has to pull in 1 word after another because the interface between the cache and the main memory is only 32 bits or 1 word wide. We will have a miss penalty of 4 times 1 plus 15 plus 1, which works out to 68 cycles. That sounds like a lot. Let's see what we can do to reduce this. One way to reduce the miss penalty is to simply increase the width of the main memory as well as that of the cache. For example, here I have shown that both of these units are increased to 32 times 4 or 128 bits of width. So if we arrange like this, then we see that this chip, which encompasses the CPU and the cache, and the main memory, between these two, there are going to be now 128 lines instead of the earlier 32. The second implication is that the processor anyway wants only one word, and if the SRAM cache is going to be 4 words wide, then we need a multiplexer in between to select between the 4 words from the SRAM cache to serve to the processor. In this arrangement, can you tell what is going to be the miss penalty for loading a 4-word block from main memory to cache? Well, since the interface is now 4 words wide, we can do everything in just one reading cycle, which takes 1 plus 15 plus 1 or 17 cycles. This improved performance though comes at a price. First, it is expensive because of the width of the memory bus. It is not easy to have a wide memory bus because the processor chip, which is going to be small, has only a certain number of pins coming out of it to interface with the rest of the computer. And the more the number of lines that have to go from the processor to the rest of the computer, the more expensive that part of the system is going to get. More than the expense, we also have a performance related implication. We have now increased the hit time from the earlier scenario because the interface between the CPU and the cache now involves a mux which was not present earlier. So there is going to be additional delay for this mux which will add to the hit time. This is not good at all in trying to solve a miss penalty issue, which is a corner case issue, because after all, for typical caches, misses are supposed to be rare, rarer than hits anyway. So in trying to solve that problem, we have introduced this other problem of increasing the hit time, which actually increases the delay in the common case of cache hits. Here is the smart solution to reducing the miss penalty without incurring the disadvantages of the wide memory solution. This solution goes by the name of interleaved memory. Let me illustrate this solution through a specific example. In this solution, we are not going to increase the width of the cache or main memory units. They are going to remain at 32 bits or 1 word. There is going to be a bus interface between the cache and main memory. This bus interface is a set of shared 32 lines. We will learn more about buses later on, but at this time you can just view them as a set of lines to convey information, and this information could be either address or data. So in this solution, the DRAM main memory is divided into 4 units. That is, we are going to take 4 different DRAM main memory units, each of, let us say, 1/4 the size of the earlier DRAM. And here is the key idea, the smart idea. We are going to interleave the blocks across these 4 different main memory units. What does this mean? We have a 4-word block. We are going to arrange such that the first word of that block is in the first DRAM unit, the second word is in the second unit, the third in the third unit, and the fourth in the fourth unit respectively. So it is not that a single cache block is resident in a single unit of main memory. It is actually interleaved in this fashion. And in this interleaving lies the smartness of this idea, because the steps in reading the block of memory is going to consist of the following steps now. The cache controller is going to send an address to memory. And because of this interleaving, the same address will correspond to different words of the same block in these 4 different main memory units. So in one single step, this address is broadcast from the cache to all 4 of these main memory units. And each of these main memory units is now going to initiate read of the word corresponding to the address given. So the address given for the first main memory block here will correspond to the first word in the block which is being read, and the address which is being read in the second main memory block will correspond to the second word in that block, and so on. So after the first step of sending address from cache controller to the main memory, each of the main memory units can proceed with the read of the corresponding word independently or in parallel. Of course, not each of the 4 main memory units can respond all at the same time because the bus width is only one word. So the actual transfer of the word which is read from each of the main memory blocks to the cache has to be serialized. So that is this third step. We are going to read the data from memory to the cache one word after another. So in this scenario, what is going to be the miss penalty for reading a 4-word block? Well, conveying the address is going to take one cycle like earlier. The bottleneck step in terms of main memory read itself is going in parallel. All of these 4 different main memory units are reading independently and in parallel. So there is only one 15 cycle instance here in this count of cycles for miss penalty. However, the last step, that is reading of the words from main memory to the cache, the actual transfer of the words is going to be serialized. So we have 4 into 1 here, and this will correspond to 20 cycles. So in terms of miss penalty, we are doing almost as good as the wide memory solution without incurring the cost of the wide memory solution in terms of width of memory. And furthermore, we observe that the mux which was present in the wide memory solution between the CPU and the cache is no more there. That is, the hit time is also not affected. So in this interleaved memory solution, these 4 different units of main memory are also known as banks. So this is bank number 0, memory bank number 0, and this is memory bank number 1, bank 2, and bank 3. Pretty smart, isn't it? Arranging the block in this interleaved fashion lets you have a low miss penalty while at the same time not incurring the cost of the wide memory solution. Well, I told you memory systems have many smart ideas. This is one of them. Once you're done appreciating the smartness in the interleaved memory idea, we can now turn to appreciating yet another smart idea in cache systems, that of multi-level caches. Using multi-level caches is a very effective idea to reduce the miss penalty. In our discussion thus far, we had asked the L1 cache to fetch a missing block from main memory. How about adding another level of cache so that on a L1 miss, you do not have to access main memory, but only another cache. So in this hierarchy of caches, L1 will operate thinking L2 to be the main memory, while on the other hand, L2 will operate thinking L1 is the processor. In such an arrangement, if there is a cache miss in L1, we will first see in L2. In most cases, the missing word will be present in a L2 block, and only in cases where there is a cache miss in L2 itself, we will access main memory to get the corresponding block. Typically, processors these days come with both L1 and L2 caches integrated within the processor chip itself. Sometimes there can be a L3 level cache as well between L2 and main memory, and this can be on chip or off chip. The advantage with this multi-level organization is that the different levels of the cache can be optimized for different things. For example, the L1 is usually optimized for hit time. So if there is a tension or design trade-off between hit time and miss rate, for L1 we will choose the design option which favors lower hit time as opposed to lower miss rate. This is because the miss penalty for the L1 cache is going to be low anyway, because we are going to get missing things from L2 in most cases. So what does this translate to? We will choose a smaller size for L1 cache which has lesser hit time but potentially higher miss rate. We will choose smaller block size which again has lesser hit time and potentially higher miss rate. We will choose low levels of associativity or even direct mapped for the L1 cache, because such a design option will have lower hit time even if at the cost of higher miss rate. On the other hand, the L2 cache can be optimized for miss rate as opposed to lowering the hit time, because hit time does not matter anyway for L2 cache, which in turn is because L2 is accessed only during a L1 miss, which we consider to be rarer than L1 hit. So what does optimizing for miss rate as opposed to hit time mean? We will choose a larger size for the L2 cache, larger blocks and higher levels of associativity, which generally result in lower miss rate even if at the cost of a slightly higher hit time. So pretty neat, isn't it? These different levels of cache all operating so nicely, smoothly to provide you that illusion we are looking for. This illusion of large and fast memory. One remark here with respect to multi-level caches is that while specifying the miss rate of a cache other than the L1 cache, we need to specify whether the miss rate is local or global. The local miss rate is the number of misses with respect to the total number of L2 accesses. Remember, in the cache system, we will try to access L2 only on a L1 miss. On the other hand, the global miss rate is the number of misses as a ratio to the total number of memory references by the processor. To test your understanding, what do you think is going to be the relationship between the local and global miss rate? As per this definition here, the numerators of these two ratios are the same, the number of misses from L2. The denominator in the second case is strictly greater than the denominator in the first case because a certain non-zero number of memory references by the processor are going to result in L1 hits, which will in turn not come to L2 at all. Let us summarize what we looked at in this video on aspects of cache performance. We first categorize the kinds of misses to caches as compulsory, conflict and capacity misses. Then we discussed qualitatively the performance implications of the various cache design options, the block size parameter, separate versus unified caches and the associativity parameter. Next we looked at two neat ideas, first of interleaved memory, the second of multi-level caches. Both have the effect of reducing the miss penalty and improving the overall performance of the cache system. In the next video, we will be looking at quantification of the program performance in the presence of a cache system.